And then there's one kind of truly dependent variable, z. Right? How would you do then? What kind of question could you ask? Can somebody come up with a question you might ask related to derivatives here, right? What kind of question could they ask me to calculate something? What could they ask me to calculate? Derivative z with respect to s. Now, how would you write that? All right, I got the z and I got the s. I need a little help on the d. What kind of d? Partial. So partial z with respect to s. Why would it be a partial? Because there's two independent variables, right? I could do it with s or t. So I better my notation better say partial of z with respect to s, because there's a second independent variable I could use. So I could do this. I could do this. Right? So what if I want partial of z with respect to s? What parts do I have to put together to get that? X and y, right? So how do I do that then? Partial z with respect to x. Let's do it in alphabetical order just to be crazy. So partial z with respect to x. What goes next to that? Just like before, but there's one thing you have to be careful about.
The partial of x and the partial.
I like it. Partial of x with respect to s. Why is this one got to be a partial now, whereas before it didn't have to be?
Because it has two.
Because x itself has two parts you could do it with respect to. Right? You do it with respect to s or t. I want s, so therefore I'm going to do it with s. Now what's the other part I can do? I don't have the whole dz ds yet.
Plus the partial
With respect to y.
times the partial y.
Partial y with respect to s. So not surprisingly, dz dt would be the same thing, just with t's here and here, right? Is that cool? dz dt would be the same thing. You have to have the x piece and the y piece, and the t part of the x piece and the t part of the y piece. Okay. Hoping you guys kind of see how this kind of goes together. It actually has a logic to it. And then you just do the parts, whatever the function they give you, do the parts you need, and throw them in there. Multiply them out, you got the answer, right? Okay. So I'm reminding myself in my head as I'm standing here, I want you guys to work on this. Let's see if we can do this semi-quickly. One side's got 12.5, the other guy's side's got 12.6.
Thank you, sir. Thank you.
So make sure you're looking at the 12 side. 12.5 side, the 12.6 obviously would be make very little sense to it yet. Just remind you guys, if you have that point about the cursive D versus the non-cursive D, use the right one here, or else it will be officially wrong. Right? So you gotta make sure you use the one for that situation. You gotta use the right notation. Alright, so let me start to catch up to you. The first few should be pretty simple, right? Number one, the intermediate variables. Yeah, x, y, and z, because they are, something's dependent on them and they are dependent on something, so they're in the middle. Number two, the independent variables there are s and t, I love it, so c. Number three, this is where you got to be a little careful when you take the derivative of x with respect to s and y with respect to s. What d do you use? Do you use the regular d, so part b, right? Z itself has got two variables, so you got to use a partial for that. So it should be 3, it should be b. Well, number 4. Now this is the one that I thought might give us some trouble. How many variables is w directly related to? 1. So when I write dw dz, it's just going to be one. It's going to have one variable, so it's got to be a regular d. You guys with me? And of course, now I got to do so. If I want, they give me w is a function of z, but z itself is a function of x and y. So dw dx. So the only thing you take w with respect to is z. Therefore, that's why I have to use that. So what I used to call hard d. You've got to use that regular d. So dw dz. But now what do you want next to that? Yeah, it's got to be something with z so that these will sort of cancel out. So partial z, and now I want it with respect to x. So that's why z is the only one you're going to use partial d's on, because it's the only one that's got more than one thing you can choose to do the derivative with respect to. You've got to use a hard d on w, because it's only got one variable in there that it's directly related to. Cool. One other way to think about it is if you write this down, think about what's the other thing that you could put there. If there is nothing else you could put there, then you shouldn't have that cursive d. What about number 5? C. I like it. C. Right? Is that everybody get that? Yeah, so let's see. 5 says the volume is pi r squared. The height changes, the radius changes, function of t, and the height negative t at t equal 1 is what I want to know. The volume changes at a rate of what? So at t equal to 1. So what I really want then, I want derivative with respect to, what's the whole thing that I want? Derivative of volume with respect to, what's
Time. T.
with respect to t, yeah, right? And what's in volume is only going to be, oh wait, did I leave the h off? Yeah.
Do.
Number 5. Yeah, there's the h, okay. Volume is only a function of t because both of its intermediates are functions of t, right? So then I can use that hard d, don't need the cursive d. Now how do you put this thing together? How could you do dv d what? dr. And then dr dt. And why is that not cursive? Because r is only a function of t. Plus dv d h, and then hard dh dt. Because h only a function of t. And I could throw all that together. Now, did you guys do it differently when you did it? And I wouldn't fault you if you did, because it doesn't say to do it a specific way. Did you just plug those in there and get a nice straight up definition of v of t, right? Not v of rh. Because you can kind of simplify it once you put them in there. So let's do it this way real quick. What's dv/dr?
2 pi r.
Yeah, 2 pi rh. dr dt, e to t. dv dh,
Pi r.
beautiful, because now pi r squared is like a constant, so it's going to stay there. Pi r squared. And then dh dt.
Negative
I like it. Negative e, negative t. That's a good old chain rule. And I can just plug stuff in there. They tell me at t equal to 1, I can figure out what r is, what h is. Right? At t equal to 1, r would be e, h would be 1 over e. And I can just plug everything in there. Right? How are we doing there? Semi-decent? Sort of decent? The more direct way to do this is you just go and plug in here. R is e to the t, so r squared would be e to the 2t, I love it, when you square, you multiply. And then h is e to the negative t, so you get pi e to the t. And that rocks, right? But if I ask you to do it using partial derivatives, you better do it that way. Don't just make your d's cursive and think that covers your ass, right? You got to do it the other way. This way, of course, is much easier. Why is it so much easier? Because there's such easy functions to work with. When you get much uglier functions, that way is actually a little easier to work with. So here, all you got to do now, what's dv dt? Same thing. Now you just got to plug a 1 in for t. Do we get the same thing the other way? Did somebody do it the other way? You did it the other way? Somebody do it the other way? You would get 2 pi e, 1 over e. Because r is e. Yep. That, right? So if you do this out, you'll get 2 pi e minus pi e is pi e. You get the same thing. Sounds like a word from a different language and shit. Alright, so that's number 5. There's a couple different ways you can approach that one. What about number 6? I'm just using this guy here, right? So they tell me number 6, x, y, natural log of 10, natural log of y, equals 10, right? So I can pull that 10 over. This is my f. So to find dy dx, I can just do that, nice and quick. Didn't like it?
I didn't get the answer.
Uh-oh. Let's see. What's this, the partial with respect to x?
Negative 1 natural log of 5. Oh, I mean, I'm putting that in there.
Yeah, so negative y natural log of y. And then the partial with respect to y, what do you have to use here? Product rule, cool. So it'll be x, ln y. Doing the derivative of this first. Done, plus xy. What's the derivative of natural log of y? 1 over y. So those will cancel, right? Let's see. And if I clean this up a little bit, where am I at? Number 6. There it is. Oh, and of course, what they did was they put everything back. Oh, let's see, what did they do? I don't know what they did.
Did you do this?
Huh?
Didn't you make this?
Oh, did I make this? No. I appreciate you thought that. If I clean this up a little bit, what do I get? Negative y natural log of y over x and y plus x. You can solve this for x. I'm not sure if that's really going to x, y, and
Solve for
ln
y
y.
natural log of x, actually.
X, y natural log of y is 10.
I would solve y natural log of y to 10 over x.
You know, all they did was they solved for something and plugged it in.
Yeah, so it's b. Oh, okay.
X ln y, x squared, let's see. Yeah, if you solve this for x,
Why would you do
well, here's y natural log of y equals 10 over x. So this top would be negative 10 over x times this stuff here. And that's actually, that's all they did. So on the bottom you get an extra x. You guys with me? So y natural log of y equals 10 over x. So that's all I did, just played around with the numbers a little bit. That then gets replaced with 10 over x. And on the bottom you get x squared ln y plus x squared. X squared comes out, it's the same answer they got. I'm not sure why what they did was necessary, but they did it.
You could just guess and throw in the negative.
I like it. Let's see. Number 7 sounds just like the one we did earlier. Let's see. So they give me x of t, y of t. Right? So the rate of change of z with respect to t at t equal pi over 4. So this is not too bad. They want this. And I can write it like that because x and y are both just functions of t. So the only thing I do z with respect to is t ultimately, right? So how do I get that? How do I put that together?
Okay, I just went ahead and I said it's 2x for cosine of t, or hold on.
Oh, so what would it look like, the form of it?
It's well, dx, dz dx, and dx dt, plus dz dy over dy dt.
And then dy dt, okay.
So it's pretty much simple.
And I just got to plug and chug, right?
Yeah.
Okay. So dz dx is nice. It's an ellipse, so it's really nice. So it's 2x times dx dt. 4 cosine t, yeah. Plus dz dy. 8y dy dt. Negative 4 sine t. Right, just plug and chug now. And again, you can plug in what x is, plug in what y is. Kind of simplify it down, like we did earlier. So x is 4 sine t, so I get equals 8 times 4 is 32 sine t cosine t. Y is 4 cosine t times 32, 128. Cosine t, sine t. I just plug in and chug it in, nothing major. So it's the same thing as before, really. You get negative. What do you get, Jeff?
96.
96, thank you. Sine t, cosine t. So you can do the same thing as before. You can make it, do they do it all the way down to that? Oop. Where am I at? Number 7. Okay, cool. Oh, and they want t equal to pi over 4, so you can just throw that in there anywhere you want to. So right here, if you have t equal pi over 4, these will both be 1 over root 2. So 1 over 2, 1 over 2 is 1 half. Half of negative 96. Negative 48. So number 7 should be 8. I love it. Cool. Number 8 is sort of old school, really. Right? Number 8 is trying to show you how nothing's really changed from before. Number 8 gives you this and then tells you, oh yeah, x and y are functions of t. So what would dy dt equal? So you can kind of go through it, and you can do your direct implicit differentiation. Right? Anybody else do it a different way? You can sort of do it a different way with what we learned earlier, but you got to throw in there the dx dt and the dy dt. You got to figure out where those go. But if you do this, you'll get 2x dx dt plus 2y equals 0, and then you can see where that goes from there. Right? So hopefully you guys realize, I would definitely expect you to just do this. This is nice. This is just straight up implicit differentiation. Right? Okay.
But in the answers, what did they do with dy dx dt?
Oh, well, that's what we're solving for. They ask, what is dy dt equal?
Oh,
So then I just solve for this, plug it in this negative, the 2's cancel, x over y, cool. 9 and 10 both use the same beginning point. And they both talk about z being regarded as a function of x and y, so the first thing I would do with it possibly, well, let's just look at this. There's kind of a way you can look at this and get the answer just by thinking about what's going to happen. if you do the partial of z with respect to x, what's going to happen with the, so if you want to solve for this, you get x, y over 10 equals z. Partial of z with respect to x, what's going to happen? What do you hold constant then? Y. So what is the partial of z with respect to x going to be?
Y over 10
So what really happened to the z? What went away?
goes to 0.
So it's sort of like you took the z and you did what to it? How do you make the x go away? Draw a little eraser there. How do you make the x go away? You divide by it, right? So y over 10 is z divided by x, isn't it? If you solve this for y over 10, you get z divided by x. Right. So the point they're trying to make there is if you have linear variables and you take a partial with respect to them, you're going to be left with something that divides them out, right? They're just going to disappear because it's going to be constant times x. Well, what's that become? The constant, so like the x disappeared, the x divided out. So actually number 10 makes the same point, I think.
Just so high.
The other way around. So incredibly enough, that would be
CY.
0 over y. Crazy.
It's 8B.
Is that only for linear?
A is b, yes. Cool.
Cool. Is that only works for
Of course, because if it was nonlinear, it would still have something left there. Like if it was x squared, it'd be 2x dx dt or whatever it is, right? Okay. Okay. So go back to this. Can somebody remind me? This is actually from section 12.2. What do these green lines here really mean? Beautiful. So as I move around them, if I were on this hill and I was walking on this line, what would be true about my path that I'm taking? Versus the guy over here is going, oh, I'm going to get to the top, and I'm like, screw it, dude, I'm tired. I'm just going to walk around and see what I can see. Right? How are our paths going to be different? What's different? What is that green line special about? As I move around it, what's changing and what isn't changing?
Z isn't changing.
Z is not changing, X and Y are. So, I like this example because what we just did was sort of figure out the derivative on these green lines, dz dt, on these green lines would be what? What did we just figure out?
0.
How much does z change if I walk around that green line?
0.
It doesn't change at all. So that's kind of interesting. In a way that kind of gets ahead of us, because we're not to the point where we're talking about derivatives or intervals or anything on a curve. What we just sort of did, we did talk about how it works as I move around this thing. The only thing we've got so far, though, is with respect to y and respect to x, right? So we had a picture like this. Oh, let me see. The first picture here was that hiking picture, remember? Oh, yeah. So this dude decides to go one way or the other, a different way. He's going to experience a different slope, a different derivative. And we had this little interactive dude, which was kind of actually nice. I cut it with a plane, and then I can see how much it's going to change. But the problem is that plane currently has to be where for this to make any sense for us, for as much as we know. Why is that plane where it is? We only know dz dy or dz dx, right? So I can only cut it parallel to the y-axis or the x-axis. You guys kind of with me? But couldn't I walk in any freaking direction I want to? Right? So if I go back to that hill, when you first get into this section, they purposely try to just make you focus on the four directions, really. This way, this way, this way, this way. But couldn't you go this way? Couldn't you go northeast if you wanted to? And we're up there saying, don't do it, the math gets ugly. Right? So I want to be able to figure out from any given point, not just parallel to the x-axis, parallel to the y-axis. I want to say parallel to any freaking given axis. What is the derivative in that direction? Right now, we can do the derivative in the x direction, the derivative in the y direction. Those are actually pretty easy. The partials, once you work with them a little bit, they're easy. Derivatives normally are easy almost no matter what. Right? But now we're talking about some arbitrary u vector. Not along an axis, but along just some vector u. What will the derivative be in that direction? So the geniuses that came up with this said, why don't we call those directional derivatives? The derivatives in certain directions. Cool? So that is the official name of these things, directional derivatives. Now, I am a big fan of trying to simplify and getting to the point. I don't know if you really agree with that statement, but I really am. And I try to do that as much as I can. There is a lot of, and I'm going to show you a little bit of this. There's a lot of trouble getting to the end result, but it is exactly what we would expect it to be. So let me kind of give you an example of where we're eventually headed. A nice concrete example. If I had somebody going this way 10 mile an hour, and somebody going this way 14 mile an hour, and I wanted to know, what am I trying to say here? At a 30-degree angle, if my x direction is 10 mile an hour, 14 mile an hour, my y direction is 10 mile an hour, what would it be along this line if I put them together along that line? How much would it be changing along just that line, right? So if I had, let me see if I can come up with a better example. If I had, let me go backwards. If I had somebody going like 10 mile an hour here, and I want to know what the components of that are, I would of course do it along the x and the y direction, right? Now this is not a hard problem. All I have to do is tell you the angle and then we're good to go. It's not a very difficult problem. And it makes total sense. It's not on either axis. So this velocity vector is actually made up of something along the x-axis, something along the y-axis. That's exactly what's going to happen. If he decides to go northeast, he's going to be made up of a part that would be what the north is and a part of what the east would be. The same way. So north I hat plus east, or it'd be j hat in that case, and we wanted to have this be y-axis, but I think you can get the components, put them back together. So that's what directional derivatives try to do. Now, the build-up to them is a little ugly. In fact, I need a little help with the picture because it's kind of ugly. Oh, where did they put my picture? Oh, okay, this is fine. So what I want here, let me see if I can manipulate this a little bit. This is kind of cool. Do you guys see this? Can you guys kind of get a feel for that, how that's shaped? Right? So if I'm standing right there, isn't that sort of like on the hump? I mean, this is the very top of the hump. But isn't it kind of sloping away as I move along? If I came from here to here, wouldn't it be still sort of like I'm on the top of it in a way? I mean, in either direction, isn't this kind of flat here? Because it's coming up this way and it's going down that way, so right there it's flat. Right? You can see that? So the directional derivative in that direction at that point should be 0 in both directions from there. Right? That's the idea. So if I was at a different point.
In the x direction?
Yeah, in the y direction, sorry. Right? I don't know if I said x direction, but no, x direction, yeah. So if I went this way from here or that way from here, I think I don't have it quite perfect, but right there, this should be flat, right? Because I'm right on top of that hump where it slopes down on either side. So if I move this a little bit, maybe change the A a little bit, there we go. You can see as I move, change the point that I'm interested in. I'm interested in the point A, B. I want to know if I move from here in the direction of u. Now you see how right now I've got u parallel to x. That's what we're normally used to. That's what we can normally handle. But the point of this section is I should be able to turn that u in any direction I want. So if I do it like Let me see something we can see. That's getting me dizzy. All right. Like that. So now I've got u kind of like right between x and y. Right? Maybe it's at a 45-degree angle. I don't know. Actually, I do know. It's 0.79 radians, whatever all that is. I want to know if I move in that direction, what will happen? We currently don't know how to do that, but it should be just what it would be along the x direction there, plus what it should be along the y direction there. That's how I put that back together, right? So it should have our derivative at that point should have something like this. The x piece put together with the y piece. Now think about that. Does that make sense? I mean, if I only do it in the x direction, I get fx. If I only do it in the y direction, I get fy. If I do it in some intermediate direction, don't I get parts of both of them together? So what I want you to do for next time.
Then equal f to u.
Second.
Is that equal f to u?
Yeah, exactly. This would be what we'll use is the directional derivative in the u direction. So we'll kind of build up to there. What I want you to do for next time is to look on page, starting at the bottom of page 12.6, and try to read through that a little bit and see how far you can get before it stops making sense. I'm trying to show you, based on the math we've done before, how do you approach this kind of math. And it gets a little ugly. And eventually end up here. All right, guys.